Welcome to this lecture series in group theory. In today's short lecture, we will introduce the group of invertible elements modulo n, and all we need to know is what is a group and what is meant by the order of an element in a group. So if G is a group and X is an element in G, then we define the order of X as the smallest natural number n which satisfies X to the n is identity. Now such an n may not exist. But if it exists, then this set is non-empty and you can take the minimum, that is the order. If this set is empty, then we define the order of X to be the symbol infinite. Okay, and we noticed that if G is a finite group, then this is always finite, meaning this is always non-empty, and the order of X is at most the cardinality of G. Alright, so this much we know, and let us proceed. Some problems for practice. And now let us get started. So let's recall this notation. If n is any positive integer, then this denotes the set of all the remainder classes modulo n, and that may be expressed like this. Right, where what does this a plus nz mean? It means a plus nk, this set a plus nk, where k is any integer. We have seen this many times. Also, we might use an abbreviated notation. In fact, almost always we will use this notation, where we are suppressing the role of n. In this notation a bar, which is same as that thing, we are suppressing the role of n, and that n will be clear from context. If there is any confusion caused, then we will try to use this notation, or maybe explicitly mention every time what this stands for, etc. Okay, let us recall Bezout's theorem, which you must know from number theory. So what does it say? It says that if a and n are integers which are relatively prime, then there is an integer b such that, well, here I must say that n is non-zero. Maybe I'll just put it here like this. So n is a non-zero integer and a and n are relatively prime integers. Then there exists an integer b such that this congruence holds. Right? This is Bezout's theorem. And it also says, or you can easily see, that if there are two different b's, let's say b1 and b2, which both satisfy that congruence, then they are essentially the same, meaning modulo n they are the same. So this much number theory I'm assuming you know. And a corollary of this fact is that if a is any non-zero integer, let me write n here. A is probably not a good idea for notational reasons. So if n is any non-zero integer and we have two integers which are relatively prime to n, then their product is also relatively prime to n. Right? So this follows from Bezout's theorem. How? Well, since x and y are relatively prime to n, you can find integers a and b such that xa is congruent to 1 mod n and yb is congruent to 1 mod n. This is immediate from Bezout's theorem. And now this gives us that xyab is congruent to 1 mod n, which implies xyab minus n times some integer, let's call that k, is equal to 1 for some k. So I'm not writing the full statements. So this implies that there is an integer k such that this happens, and therefore the GCD of n and x times y should be 1, because the GCD divides the left hand side and hence the right hand side, but the right hand side is 1. So all this you must already have seen in number theory. I'm just recalling. Okay, let's move on. So again, recall, for any integer n at least 2, maybe for n equals 1 also you can do everything, but that would be rather silly. So let n be at least 2. And then we had this map. We have seen this map earlier. What is this map? It just takes a bar comma b bar to ab bar. And there is an issue of well-definedness here. So if you pick a and a prime such that a bar is equal to a prime bar and b prime such that b bar is equal to b prime bar, for this map to be meaningful, it must hold that ab bar is equal to a prime b prime bar and That is true, that does hold because of basic modular arithmetic. So this map is well defined, and hence we have a binary operation on Z mod nz, namely the dot that is above. So this is a candidate for a group, but this is not a group. This is not a group because there is no inverse. I mean, this is one reason why it is not a group. There is no inverse to the element 0. The element 0 bar. What is the identity? The identity of this guy is 1 bar that you can easily check. That is the only candidate for the identity. That's not difficult. And what else? Yeah. So now 0 bar has no inverse because 0 bar dot x bar cannot be 1 bar because this is 0 bar and we have assumed n is at least 2. Okay, so this is not a group, but we can throw away some elements from this guy and make it into a group. So for that, we define Z mod nz star as those things in Z mod nz. Let me write x bar such that there exists y bar in Z mod nz with the property that. So the problem that arose in this being a group, we are just trying to forcefully fix it, right? So yeah, instead of writing this, I could have also written xy bar because that's the same thing. Okay, so this is how we define Z mod nz star. This is a group. So I think that is the next lemma. Yeah. So this is the group. I mean, this is a group. And let's prove it. So associativity is fine because this binary operation is associative. That I did not mention, but we had seen this earlier. Associativity of the binary operation is fine. First, I mean, even before talking about associativity, what is the binary operation? We had a binary operation on this full thing. What about this guy? What is the binary operation on this guy? Well, same as that, just restricted. So maybe I should first talk about the binary operation. So note that by what we saw in the previous slide, by the discussion in the previous slide, or maybe before even I mentioned that, let me make an observation. Note that Z mod nz star is precisely the set of all the x bars such that first of all x is an integer, of course, and GCD of x and n is 1. That's Z mod nz star. The reason is very simple. If suppose x bar lies in Z mod nz, we want to show if this happens, then by definition of Z mod nz star, there is some y such that this equation holds, which reads exactly that xy is congruent to 1 mod n. But that would immediately imply that n and x have GCD1 by a similar reasoning as we saw in the previous page, because this means that xy minus nk equals 1 for some integer k, and hence x and n have GCD1. So anything here is definitely here. Now, if something is here, it is also there by Bezout's theorem. So this observation is crucial, but not difficult because we know the basic things. And now, further note that the multiplication, the dot map, if you just feed it a pair from Z mod nz star cross Z mod nz star, it will output something in Z mod nz star. So I don't know how to write that, but you get it. So if you have x bar, y bar, what does it output? xy bar. As of now, it's just an element here. But since x has GCD1 with n and so does y, meaning x and y are relatively prime with n, therefore so is xy. We saw this in the previous page. And hence this is also there in Z mod nz star. Right? So this is a genuine binary operation. I'll just write it that way, is a binary operation. I don't know how else to write it. And now it makes sense to ask if this is a group under this binary operation, which is multiplication. And the fact is it is, because associativity is fine, it was already present. The bigger thing was associative, this whole thing was associative. So that is fine. Identity was also fine. The only problem was the inverse, and that we have fixed, right? So the problem was the inverses. We have forcefully defined Z mod and Z star so that everything has an inverse. And the thing that makes it click is that even after restriction to this set, that the binary operation above remains a binary operation. That is the main technical input here, which was covered in the previous slide. So inverse is inbuilt, right? And also from this comment, it is clear that Z mod and Z star has size same as phi of n. Now what is phi of n? This is the Euler's totient function, which I am assuming you are familiar from number theory. What is the definition of phi n? Phi n is those integers between, so those integers which are between 1 and n and which have GCD 1 with respect to n. So that is the definition of phi n. Why is this guy having size equal to phi n? Because what is this set? This set could have been rewritten as x bar. X is an integer, of course, but you can always insist on this much. We were running over all integers here, but if you just run over in the first n natural numbers, that's enough. Modulo n, everything will be covered. Okay, so that's just immediate from that we see that this has size equal to phi n. Okay, and I'm assuming all of this thing you already knew from number theory. All right, so today my slides are not that good looking, but it's okay. Or one day it's fine. So let's do one more thing and that will be it. No, I think we'll do two things. Let's just compute out this example. So we have this group Z mod 7 Z star. Let's compute the inverses and compute the orders of all the elements. So what is the inverse of 1? Well, 1 is the identity. So the inverse of 1 is 1. What about 2 or 2 bar? What is the inverse of 2 bar? It's 4 bar, because 4 times 2 is 8, which is 1 modulo 7. 3, I think it should be 5, because 3 5 is the 15. Right, and now everything else we can symmetrically fill out. 6 has its inverse. 6 is its own inverse. Okay. Now what are the orders of everything in this group? The order of 1 is of course 1. It is the identity element. The order of 2. So to see the order of 2, we have 2 bar square is 4, while 2 cube is 8, which is same as 1. So the order of 2 is 3. What about 3? We have 3 square is same as 2, because 3 square is 9, which is 2 mod 7. 3 cube is therefore 6. 3 to the power 4 is therefore 18, which is 4. 3 to the power 5 is 12, which is 5. And 3 to the power 6 is 1, because 3 5s are 15, which is 1. Just verify, this is simple computation. So the order is 6. And what is the size of Z mod 7 there? It is also 6. So interestingly, there is an element of order 6 present in this group of size 6. And later we'll see this is a general property. Whenever P is a prime, Z mod P Z star always has this property that there is an element of order P minus 1. It's very interesting, but for later. Order of 4 bar, or order of 4, which is because 4 is the inverse of 2, its order is same as the order of 2, so we can just directly write 3. For 5, we can write 6, because the inverse of 5 is 3, and order of 6 is 2, because 6 square is 36, which is 1. So just some computation to get a feel for things. All right. And lastly, a small application. It's not much of an application, but Anyway, we saw this result earlier that if we have an abelian group G and X is any arbitrary element of the group, then X to the power mod G is identity. We saw this earlier. And this was the proof, if you want to refresh. And as an application, suppose n is any integer at least 2, a is relatively prime to n, then a to the phi n is congruent to 1 modulo n. So this is Euler's theorem, right? Euler's generalization of Fermat's little theorem. He of course didn't prove it in the language of group theory. So why is this true? Well, let's just use this theorem. A bar is an element of Z mod n Z star because A is relatively prime to n. And thus A bar to the power size of Z mod n Z star by the previous lemma. This is same as the identity of the element, identity of the group, which is 1 bar. And this implies A bar to the power phi n is 1. But this is same as A to the phi n bar is equal to 1 bar. And this equation and that congruence are exactly the same things. So it's a straightforward application of this particular lemma, but I still wouldn't call it an application because what is the proof of this lemma? The proof of this lemma is what is usually given as a proof for Euler's theorem or Fermat's little theorem. So as of now, I wouldn't really call it an application. It is just allowing us to see that group theory packs in a lot of number theory in it. Later, we will give an alternate proof of this guy, which is generally not covered in number theory courses or a first course in number theory. We will see this as a consequence of Lagrange's theorem, which is a truly group theoretic statement. And hence, after seeing that, we can call this an application into number theory. And we'll see many more applications to number theory of this machinery. So this is all that I wanted to say. As usual, like, comment, share, subscribe, and I will see you next time.